All right, I think we're going to get started. John, if I'll go here with the next slides.
Okay, good morning, everyone. Thank you for attending this webinar. It's the second in the series of discussions about the calibration assistance tool. I'm John Donahue. I'm the current chair of the AASHTOWare Pavement ME Design Task Force. The presenters today, Applied Research Associates, will be Wouter Brink, Chad Becker, and Harold Von Quintus. Just a reminder, too, is that this presentation will be available for viewing on the Pavement ME Design website that you see the link to on the slide. And just some reminders, all your phones will be muted. If you have any questions during the presentation, you can enter them. There's going to be a Q&A box. But don't mistake it for the chat box. Please try to put your questions in there specifically in that box. The presenters will answer all the questions or try to answer all the questions at the end of the webinar. Now, someone who's not presenting at the time you submit the question may be able to answer it while the other speaker is doing the presentation, so you may get an answer before then. But if for some reason there's any questions that can't be answered because of time, those will be handled separately, but we'll make sure that we will get to everyone's question. Just to kind of recap how the software improves over time, we do take suggestions, we being the task force, try to get as much feedback as possible. I think we've improved this process over the last several years, especially through the use of the ME Design user group, which is meeting again in a couple weeks in New Orleans. The task force tries to do a comprehensive job of monitoring any active or completed research, typically from sources like insure projects, some federal highway-sponsored research, and then sometimes state pool fund projects as well. But anything that can be sorted out and turned into a product that can be integrated into the ME Design, we're definitely on the lookout for. The task force itself, you want to go to the next slide, Wouter. This is the current task force membership. You can see the members on there. We have Vicki Schofield, who's the AASHTO project manager. We also have several liaisons from other groups as well. The task force rotates over occasion. Well, it periodically drops somebody off, and so there are new members coming on board. We just unexpectedly lost a member last month when she changed positions, so she had to resign her position on the task force. So that's one we'll be filling. I myself will be rotating off next June. So there are opportunities in the future just to keep in mind for a state member that's a licensee of the AASHTOWare software. You will have future opportunities to be a part of the task force if you'd like to. And this, as I said, this is the second to complete the webinar series on the calibration assistance tool, the last one being about a week and a half ago on October 10th. We'll be picking up, I believe last time we left off after going through the verification process with the global coefficients, and now going through the analysis of that to determine if local calibration is necessary, and then coming up optimizing the local calibration coefficients, and then finally going through a validation process to check those. That's what today's webinar is going to cover. There will be a third one to complete the webinars for this fiscal year, and that will be sometime in February, and that will be after the top-down cracking, the 2.55 version of the software comes out, and that'll have the new asphalt top-down cracking model. So we'll have a webinar to discuss that development as well. And with that, we'll turn it over to our speakers.
Thanks, John. We're going to do one poll with 2 questions. I think Chad's going to open that up. Should be about a minute to answer. It should be open now.
Somebody's not seeing the poll question.
Yeah. Need to open up the poll. Okay, about another 15 seconds here.
That was the case.
Gonna close on that here. Hold on.
All right. All right, just to give an outline of what we're going to go over today, I'll give a quick review of what we did in our webinar from 2 weeks ago, just a part 1 review, and then we'll go into part 2 of the Calibration Assistance Tool webinar and examples and walkthrough. All right, so just as a quick overview, a fully featured web application was developed. It has a calibration database associated with it, with both LTPP and your user-defined pavement sections. Also a step-by-step calibration guide document and a software manual, and it should be available tomorrow. That's for use with current Pavement ME licensees. Last time we went through the full introduction, why it was developed, what was developed, the reasoning for it. I went over the requirements, assumptions, and limitations. I also went through the overall calibration process that was adopted and developed for the calibration assistance tool. And then I did a software walkthrough, and that walkthrough consists of going through the login screen, the home screen, navigation pane, how to upload your required data, and then we started a new calibration project for the parts 1 through 3 of the calibration process, which basically ended with reviewing the initial verification results and deciding if calibration was needed. So for today, we want to go through the remaining portions of the calibration tool, and we start by looking at the management of your calibration project. So if you have multiple created, how to open those up, adjust things, go back and forth between different calibration projects that you've performed. Then we'll go just a quick initial verification review that we did from part 1, just to look at the model statistics, if we needed calibration or not. Then I'll go through a detailed verification review and kind of go through all the options and methods you can use the tool to gain knowledge about your pavement sections, what trends you are seeing, and how to make decisions from the data. I'll go through some optimization examples where I change some coefficients and how the data and the predictions improve, or how the changes in coefficients impact your predicted performance and how that compares to your measure. And then I'll go through the final step, which is the validation and the data export of the calibration tool. Okay. The first thing I want to go through is the is how you manage your calibration projects. So within the home screen, you will see a button that will say manage existing calibration projects. Once you click on that item, it will take you to the screen where it'll list all of your own projects, where you can distinguish between what you've created before. So for this one, I can only see webinar 1, parts 1 through 3, because that's what I created previously. Created date, it shows which types of pavement sections were used, if it was LTPP or user defined. And it'll tell you unit system, and some of the actions include, you can view that project, you can share it with somebody else, which will create a copy for that user where they can then review and adjust coefficients using the pavement sections that are included in that project. They have no way to edit those pavement sections because they do not own those DGPX or pavement sections, or you can delete that project completely. Now, the other option or other window that you'll see is the projects that have been shared with you. So in this instance, there doesn't show anything because nobody's shared any projects with me, but that's where those projects will show up. And they basically create a local copy that you can use, and it won't impact what the other user that shared that with you, it won't impact their project. Okay, so what we'll do, what I've done is we basically will view that project and then edit it as we go. What I first want to go through is part 4. We did kind of briefly go over this last time, but the main focus of part 4 is to review your hypothesis test results. Once you have done your initial verification runs, you determine if calibration is needed. If it is not needed and all of your hypothesis tests pass, or your standard error and your bias is low, then that is where you stop. So one item that would be helpful is, say if we have future versions of the software, you can run it through the calibration tool and then quickly determine if those changes in the software impacts your calibration coefficients or if you need to adjust. That way, you don't have to go through the whole process if there were no significant differences between the measure and the predicted data. Now, if calibration is needed, that's where you now select the coefficients and you move forward, and you can modify the specific coefficients for each distress type. And the automated steps is here. It'll calculate and compare the predicted and measured distress, assess bias, standard error, and perform the hypothesis testing. So as a review from last time, this is the final screen we saw, and we look at our descriptive statistics where we summarize our bias, our standard error of the estimate. We have our model fit statistics with the intercept, the slope, and then our final hypothesis values. So we have our measure versus predicted. We have our descriptive statistics and our final hypothesis test results. And as we can see here, all of them were significantly different than our null hypothesis. So we recommend performing local calibration on these pavement sections. Okay. Now, before we actually go into changing any coefficients, we need to determine why we are seeing what we are seeing. So what can the measure and predicted data tell us to identify which calibration coefficients to change, identify outliers. We need to use all of the features within the software to gain knowledge about your pavement sections and investigate why certain sections perform the way they do. Use the data filters to update measure versus predicted plots, time series plots to identify trends and make decisions about those pavement sections. So I have quite a few examples here of things to look at. The first one here, as you as I showed previously, just the measure versus predicted plot, we can see certain data points that are kind of beyond or stand out to us. So some of the questions you want to ask when you look at all this data is, why are these points so different than the rest? Do they have any structural differences? Are they in different regions within your agency? Do they have any features that are unique to them? Did they exhibit any material related defects or stages? Was anything that stands out? So you need to know what your pavement sections, the characteristics of those pavement sections, in order to make these decisions. So what can you conclude from the time series data? Is there any significant differences between the conventional trends that you've seen in other pavement sections? So these are the questions that you want to be able to answer as you go through the calibration process. And some additional ones I've added, if there are differences, do those differences significantly impact your residual error? You can look at your analysis of variance table to look at all those input variables that specifically or that correspond to those pavement sections. And then you need to make a decision on, should these sections be excluded or do you keep them in the calibration data set? And one thing is, you want to be able to explain why you're seeing what you're seeing. Now, this may require you to go into your historical records and identify something specific to that particular pavement section. And you can do this before you even get to the calibrator when you identify and select your pavement sections. Let's see. Okay. So I want to highlight some of these pavement sections. So we can see with this particular highlight here with the label, you can see that the actual measured distress increases while your predicted rutting almost stays constant. I mean, it ranges between 0.6 and 0.8, or a little bit less than that, while your measured keeps increasing. So you need to be able to tell why that is happening and what is the cause. And then you can decide how you can adjust the calibration coefficients to remedy this, or if this is basically an outlier. One thing you want to make sure you look at is, can you explain that? If you can, then you can exclude the section if it is an outlier. And if you cannot, then you want to keep that section in there because you don't necessarily know why it's performing in that way. Now, if we look at the residual error, what you're going to see here is our average residual error is going to be close to 0. But as you can see here, that doesn't necessarily mean that you have an unbiased model. So what you see, we have over prediction and under prediction, which then overall gives you a fairly low bias. But you need to be able to look at this data and see that, okay, well, there is still a systematic bias or effect as you increase or as you have higher predicted rutting, your bias also increases. So it's you want to be able to account for this. So why does it look like that? You want to know if those residual errors is randomly scattered around 0 without any direct trends. And then you can look at how can I correct this, and you can do that by changing a combination of calibration coefficients, BR1 for rutting, BS or BR2 and BR3. And we'll go through some of those examples of how to try to mitigate and adjust this residual error to be less dependent on the predicted error. Okay. So since all of those pavement sections represent three different agency or three different LTPP sites or locations, it's from Florida, it's from Alabama, or Florida, Alabama, and Arizona. So what I want to do is kind of split those out into individual agencies and look at which ones represent, or if we can find any additional information for each section. Can we explain why we're seeing that residual error dependent on the predicted error? And then can we identify why they're performing the way they are, and should they be calibrated separately? Okay, so we're looking at here is only the Alabama sections. I think there were about 5 or so from the SBS1. One thing to note for all these sections is they're in close proximity of each other. They have basically the same climate, same traffic, same subgrade materials and conditions, and the only thing different could be their thickness. Now we look at the data here, you can see the one that's highlighted in 1 performs very different compared to the cluster in number 2. So what is the difference in this section? Was there any material defect during construction? So you want to go look at your records to see what was documented. Was there a loss of bond between the AC lifts, or was there any other impacts or construction-related issues, or a number of other factors that could affect that particular section? Now the question is that an outlier? And it's only an outlier if you can explain the difference. So if you know why it is performing the way it is, then you can delete this section. Otherwise, it should remain in the data set. So the measure versus predicted is not the only way to view or use the calibration tool to gain additional knowledge of your pavement sections. So the next one we want to look at is the time series data. Here you can see for that particular section that you have a clear difference between how rutting accumulates over time. So you'll see here is an increase in the slope, where as time goes on, you get a lot more rutting. Now, why is that happening? So this is where you can look at material-related defects. Was there stripping, loss of bond? And we can clearly see that that particular section performs very different compared to the others. And for this example, we're going to assume that we can explain just to move forward, and we recommend that it should be excluded from this data set. Okay. So now we can repeat that process, and that's why the tool is a iterative analysis and decision making, and the user needs to be able to identify and really become familiar with what's in those pavement sections. Now we repeat that process, so we excluded that pavement section, and now what? Now we go through the exact same process, look at, it looks like there's a slight under prediction as measure rutting increases, and do these sections have different thicknesses? Can that explain some of the bias? And we can further use those filters within the software to kind of look at what is different between them. So here it's kind of all the traffic's the same, all the subgrade conditions are the same, the climate's the same. So the only difference between these sections could be their thickness. So for this data, now we're going to split it by thickness specifically. So here I split it between the AC thickness greater than 10 inches, which as I presented last time, that is one of the experimental design matrix items or categories, primary factors. So I'm able to kind of split them based on those conditions. So as you can see here, for the pavement sections that are greater than 10 inches, you will see as predictions or as your measure data increases, your predicted data does not increase as much. So how can we adjust the calibration coefficients to improve the prediction capabilities and get this and get the data to be more along the line of equality, the red line here. Now, if you look at the time series data, you can also see that it's more a difference in magnitude than a slope increase as you saw for that one section that we excluded. Now, if we look at the pavement sections that are between 5 and 10 inches, it performs different, where we have it over predicts rutting compared to the pavement sections greater than 10 inches. And then same thing with the minimal difference in slope here, where we can kind of, they're almost the same. It just needs to be translated up and down a little bit. And how do you adjust your calibration coefficients to account for that? And that's where the guide, calibration guide, goes through the process for looking at the impact and the sensitivity of the calibration coefficients with respect to the predicted data. So now you can see maybe for the thickness is greater than 10, we want to look at our BR2 and BR3 and even BR1, while for our thicknesses of 5 to 10, we could look at BR1 only, or we can look at our subgrade coefficients or our granular layer coefficient BS1 and BSG1 to kind of shift to bring those values down for those sections. And the biggest takeaway I want you all to get from these examples is the types of questions that you should ask and how to use the tool to gain that knowledge about your sections and how to use that information to guide you in adjusting specific calibration coefficients. Because you could change all of them at the same time if you want, but it does not necessarily mean you're going to get a better prediction or improve the overall capability of the models. Okay. So next one I want to go through is just some of the Florida sections and how you're going to see a very different performance compared to what we saw in the Alabama. Here we can see that some of these sections, there's almost, it looks like there's clusters of data for each prediction section. So you need to know and identify why this is occurring. So what's different between these sections? Do they have different base types? Is one an asphalt treated base? What's the different thicknesses? Is some of them thin, some of them thick? Maybe what's the impact of the subgrade or the granular base layers? Because you need to be able to explain and see what's happening with these sections. And I did the same analysis as I did with the Alabama sections, where I split them by less than 5 inches, between 5 and 10, and then also greater than 10. And clearly you can see that some of these are performing very different. So even for the thicknesses less than 5 inches, there's some bias here where you can improve the overall predictions, whereas it underpredicts for this particular section. It's I think it's a GPS 1 section. And then we look at the 5 and 10, we see two clusters almost, one that overpredicts and then one that underpredicts. And then for the AC thicknesses greater than 10, the majority of the sections underpredicts as a pavement or rutting. Now, one thing that is different between these, you can see that there is a thickness effect, but how do you account for that? I'm just highlighting some of these points. There were findings in the NCHRP 930A where there is the confinement factor that's embedded within the calibration or within the pavement ME design model could overestimates the impact of confinement. That study did go into one way to account for that is to change the lab-derived K values, which you will have to do outside the calibration tool, but you can do within the pavement ME design, and then re-upload those pavement sections. So that's one way to adjust for the confinement, or if you see these thickness differences, because the model itself does not directly account for, model coefficients can't directly account for thickness differences. So that's something to look at your data, to really study what's going on, and be able to explain why you're seeing what you're seeing. All right, so those are the examples that we wanted to make sure you look at what's going on, assess, and use the tool to your advantage to really dig deep into what your performance and what your predictions are showing, and from a calibration standpoint. So as a recap for part 4, user decisions, you need to carefully review your measured and predicted data to gain knowledge about what you're seeing. Use the filters to make your decisions and to identify trends, outliers, differences in performance, why one section's performing different than another, and go through the iterative process. I mean, this is not going to be a one-click solution where, oh yeah, it's just going to be great. You want to really go through and iterate to identify all of the different intricacies that could be observed within your pavement sections and the calibration process. Now, the automated processes within part 4 is, I mean, the software populates all the data tables and plots. It calculates the descriptive statistics and model fit statistics, does the hypothesis test, populates all the different data, and filter data and update figures and tables. So it makes it quick and easy to review and look at your calibration data in a way that can help you make decisions. Okay, so the next part, so now say we've already identified why our sections are performing the way they are. We've explained all those differences. Now we can move to the optimization and changing the coefficients to reduce the bias and improve your standard error. So parts 5 and 6 of the calibration process is to select the coefficients, identify, execute the optimization runs, and iteratively move through the process of refining and adjusting your coefficients to get the best fit. Step 6, or part 6, is to basically review your final coefficients and export all of your data and import that to Pavement ME. So from an optimization standpoint, the main screen is going to look fairly similar to your detailed review, where initially you're only going to see your initial verification results. So it'll have your bias, your standard error, and your measure versus predicted, and the residual error corresponding to those pavement sections, and your descriptive statistics like you've seen in the initial verification. So all of that builds on one another, so can compare them fairly easily. So next, you want to move through the process to adjust the coefficients. So here's the Alabama example that I just showed previously. We have excluded that one outlier section. And we can see the measure versus predicted, just like we did before, and our residual error. So as you can see, the residual error is still dependent on your predicted data. As it increases, over predicts for higher predicted values while it underpredicts for lower. Now, one way to identify which coefficient to change specifically is to look at the regression analysis table, where you can select the different inputs that were selected in the experimental matrix design, where you have your AC thickness, total AC thickness, your binder type, mean annular air temperature, traffic, subgrade type, data source if you have multiple data sources, and your subgrade modulus. So I only selected AC thickness here because for these pavement sections, the mean annular air temperature from the climate file is like the same, the traffic's the same, subgrade type is the same, and we only use LTPP. So there's no difference in the data source. And so we update the model and run the ANOVA to see if this particular input or variable has a significant impact on your residual error. And for this case, it actually is significant because it's less than 0.05. So it's we want to kind of adjust some of the coefficients to see if we can reduce the bias and remove that systematic difference that we saw in the residual error plot. So as we move forward, if you keep scrolling down in the software, you'll see the coefficient adjustments. So first, we're going to kind of adjust and improve, see if we can reduce the slope or improve the slope of the AC raw model to better represent our payments measure performance. So what you do, you go to that particular AC running BR3 coefficient, we select new value, we enter a minimum value, a maximum value, and the number of increments to iterate through. We click on Run Optimization. This will send it to the analysis server and automatically run all of those combinations for each project in the calibration set. This is a time where it may take a long time depending on how many coefficients you're changing at the same time, but also how many increments you're using. As I mentioned last time, we presented a table of if you're changing all 5 coefficients and you have 5 increments for each, that could take up to 100 days if you have 100 calibration projects. So the software will actually not allow you to run any projects greater than 60 hours for total runtime, and it'll inform you to contact us at ARA to release that project and run them. But as you go through the process one by one, it will not take too long if you just change by 5 increments or 1 or 2 coefficients, because you will change them simultaneously at times. But one way that I've done it is to kind of set your initial minimum and maximum fairly broad, and with 5 increments as a max, and then determine based on the results if you need to refine them further. And that is illustrated in the next screen. So once it's done running, the software will tell you, you click on that particular calibration run, iteration run, and it'll show you the 5 different sets of coefficients that it ran. So you can click on each one where it will update your measured data, your predicted data, populate your residual plot, as well as update your descriptive and model fit statistics and hypothesis tests. One nice thing you can also look at is it will show you your bias, your standard error of the estimate, as you increase or decrease your calibration coefficient sets. So what you'll see is you'll have bias and standard error for each set, and that shows up on this. Once you've removed the systematic bias, you can actually see that here, I think this bottom line is the zero value. So you can see between sets 1, 2, and 3, it crosses that zero bias value. So you could further refine based on between those two sets. But what we'll see when we look at our measure versus predicted and our residual error, we see that we still have that systematic bias, and that was not removed by just changing BR3. So you might need to go back and adjust BR1 or BR2 or even the BS1 and BSG1 to attempt to reduce and bring these values more in line with as a random residual error, so it's not increasing with increasing predictions. As you can see, now we are slightly over predicting compared to what we did before, and I have those examples here where we can look at the initial verification, where we see that most of our data fell below the line of equality, and after the BR3 was updated, now we see most of these sections are above. But one good thing is the values in their residual error has spread out a little bit more compared to where it was all just clustered between very small values of predicted data. So now we can adjust the next time to address and maybe reduce the standard error and improve the scatter among the or around the line of equality. All right. So the next example, I want to go through just some of the Florida sections and what we've seen here. So it's the same process. I've run a couple different iterations of the calibration coefficients. We see here at the measure and predicted, and the residual error plot is from the initial verification. So it's the same exact process. Now, when we look at the ANOVA table here, I looked at the AC thickness, the mean annual air temperature, and the subgrade type. And what we can see here is thickness does not necessarily have an impact, while mean annual air temperature and subgrade type seems to have a significant impact on your predicted or your residual error. Now you can do these individually or look at the confounding factors, or if there's if they have interaction effect. But based on this, since I saw mean annual air temperature did have a slight effect on your predicted or your measure and predicted residual error, I changed the BR2 coefficient and I arranged it from 0.52 to 0.6 and increment and 4 different increments. And from that, you can see the one that fit lowest standard error and bias. Now it overpredicts on average for the majority of those sections. One interesting thing from the residual error standpoint is you can almost see those different clusters, but there's 3 different data sets in here, which could be attributed to the depth and confinement factor that may be overestimating the impact of confinement on total running. As a comparison, here you can see the initial verification. So the slope did increase for each section, but we still did not solve the residual error trend. Now we have these slightly different clusters for the different sections, and we'll have to address that in another way or combining different coefficients to improve upon this model. Let's see. These were the examples that I wanted to show for the optimization. Now, this is a very iterative process. You'll go through many iterations to guide you to the right calibration coefficients. From a user decision, you need to select which coefficients to adjust based on what you see in the data. You need to review your results and determine if those adjustments are needed. Iterative process to look at how your standard error and your bias is impacted by the different coefficients. And the automated processes are just, it'll send you those data sets and list of projects to the analysis server for execution. It'll run all those sets, extract all the data. It'll notify the user when the optimization runs is complete, and it'll populate the results for you as you go through the iteration process. Now, once we have done all of the iterations and we have selected our final, we're okay with how the calibration came out. Our measure versus predicted looks pretty good. Our standard error is pretty low. Our bias is almost zero. No systematic difference or bias. Then we move to our final selection and the part 6 of validation and export and developing our standard deviation of residual error relationship and our coefficients for use in pavement ME design. So as an example here, it shows you kind of just the different iterations that I've run. Now, okay, well, for this particular data set, our bias was almost zero, while our SE standard error of the estimate is 0.13 inches. It's fairly low. I also want to note here how long some of these runs can take. So say here I started a couple days ago, 9:31 p.m. All the analysis runs finished around 11. Somewhat depending on how many coefficients you change and how many sets you have, it can take not too long. This one took about 20 minutes for 3 different coefficients. This one took about also 20 minutes. It depends on what the server usage is at that time. So it doesn't take a very long time if you change one coefficient at a time. Now, if you have 25 different sets, it may take a little longer. But the nice thing is you don't have to wait for it to complete. You can come back to it when it's done. So now, once you click accept, so all of these options, you'll have a view or accept. We accept this particular run 5, and we move to the next validation part. So what you'll see is it'll actually show your verification results, it'll show your calibration results, and your validation results. Validation results will only be displayed if you have more than I think 30 total pavement sections in your calibration. It's a random split sample, and you'll see that during the optimization parts as well. And here it really gives you a good indication of how they compare from verification, what was the model improvement, or if there was and then your validation for your independent data set that's not included in your calibration. You can still go back. So if this is not acceptable and you still think you can improve, you can always go back to the optimization and further refine your coefficients and try to improve the predictions even further. Now, once you have reviewed and you're okay with all of those predictions, you can go to the next step, which is to define your standard deviation residual error formula. So each pavement model has its own standard deviation of a residual error equation. This gets used in the reliability. So all of the calibration is done using the mean predicted values, and then we derive this formula to add in for all the uncertainty in the predictions, measurement, everything. And the way it is done is we look at all of our distress data, measure predicted our residual error. We divide the data into bins and plot the standard deviation of residual error compared to your average mean predicted values. So for each bin, you'll have a data point for standard deviation of residuals and your average predicted, as you can see here. For the running model, it uses a power function to represent the standard deviation of the residual error, and it'll adjust the coefficients automatically for you. Now you can review what that standard deviation looks like, plus the optimized coefficients that you've selected in this case. And then that's basically the final step. Once you're happy with this particular model, you can then export your verification results. So you have your verification data. You can export your optimization data, which will include your measure data, your predicted data, all of the factors that were included in the analysis of variance table, and then you'll have your validation data as an export as well. The coefficients can then be exported as an XML file, which you can then directly import into Pavement ME. We try to make this as easy as possible to use your calibrated data and directly import and use them in Pavement ME.
So just to tag on to that, the coefficients XML output button that's in the tool will actually output an XML file that can be loaded directly into Pavement ME Design.
Okay, just a Part 6 recap. We review our final coefficient selections. We compare the verification, optimization, and validation results. Was bias eliminated? What did the standard error, the estimate reduce compared to the global models? Did all the hypotheses have a p-value greater than 0.05? And are these results acceptable for your agency? The automated processes, like in most, populate all the data tables, calculate descriptive statistics. It'll derive the standard deviation of residual error equation based on the models that are currently in Pavement ME. So we're not changing the form of the standard deviation equation. So for rutting, it's a power model fit. For bottom of fatigue cracking, it uses the exact same formula. It's a sigmoid function based on the damage predicted. For thermal cracking, it is a linear model for the different levels. And then it allows you to export the results so that you can verify or look at the data on your own. And also import your exported calibration coefficient directly into Pavement ME. So you can either use it as a import to a specific project or create it as your default calibration files. Okay. With that, I just want to go over just what we've done in the last 2 webinars, parts 1 and 2. We went through all the different steps in the entire calibration process, where we have our part 1, which is getting ready for calibration, where you establish your sampling matrix, select your pavement test sections, you populate the matrix from the calibration database or your user uploaded sections. Then for step 2, you review your distress data, you extract and review that, calculate your distress data statistics and identify some outliers, decision on adequate number of test sections, you calculate that. Next, you go to part 3, which is select your calibration coefficients for initial verification. You can either use the global coefficients or import previously created or derived calibration coefficients. It'll run all those projects that you selected and let you review project files and extract and populate your measure versus predicted, your standard error, assess the bias, perform the hypothesis test, and then you can decide if calibration is needed or not. If it is, you do additional detailed review of your measure versus predicted, like we went through today, to identify and gain knowledge about what your sections are showing. And then we go through parts 5 of optimizing the coefficients to eliminate that systematic bias and improve your prediction capabilities. Once that's done, you've selected your final coefficients, you review your validation results, develop your standard deviation of a residual error relationship, and export the data to be used in Pavement ME. And just to further iterate over what we've said in the last couple meetings, as I've also demonstrated today, it is not a hands-off approach. It requires significant user interaction and decision to really understand what the data is showing you, how your measured performance and predicted performance can be used to improve the model capabilities. Not a one-click solution, and it does not identify and select these sections for you. You have to do that prior to using the calibration software. Data quality and accuracy must be checked before using it or characterizing your pavement sections in Pavement ME. As a reminder, we'll be doing a live demonstration at the ME user group meeting, which is in about 2 weeks, November 6th and 7th in New Orleans. And we have now one more poll question before we move to the question and answer session.
Okay, so that poll should be open now. About another 15 seconds left on this poll.
All right, well, with that, we want to open it up to questions and answer session. I know Harold's been answering questions as we go. Chad, do you want to?
Yeah, so I'll go through just some of these general questions. I'm sure Harold's going to have a couple answers as well he might want to expand on. For future webinars, if you're not seeing the poll questions, we had a couple people have trouble with that. There should be a panel for that inside of the WebEx plugin for your browser. So just check the controls for that. It should be in there. We had a question asked if the software is available for folks who have the educational version for teaching purposes. The answer to that currently is no. The tool is only available for workstation or site licenses. And I sought some clarification, or will seek clarification on that from the task force as to what the plan there is. Another question about a report or manual available to help users use the calibration assistance tool. The answer is yes, there are 2 documents available. The first document is the guide that describes the calibration process from an engineering perspective using the tool, and the second document is the user manual, and that describes the various features and functionality of the application. If you want to answer, you want to go over Tom's question, Harold, or?
Which one? Number 2.
I guess we'll just go in order here, so maybe it's the first one.
Okay. Okay, there was one question, let me make sure, that had to do, oh, I remember. One first question had to do with how do you define the plastic deformation coefficients, the percentage within each of the layers when we do not know what the actual rut depths are within the individual layers. And very good question, very appropriate questions, because for most of the LTPP sites, without the forensic investigation, you really do not know what the plastic deformation is within each of the individual layers being the individual asphalt layers and or the subgrade, aggregate base, and asphalt layers. And without trenches, we do not know. So the process, what was done for the global calibration, is the same process that was used in NCHRP 140D that Matt Witzak originally set up for looking at defining the plastic deformation within individual layers themselves, the asphalt layers versus the non-asphalt layers, the unbound aggregate base and the subgrade. So the same process is being used that Matt recommended from NCHRP 140D. However, it's always recommended, especially for the thinner asphalt sections, that trenches or some forensic investigation be completed to define what the rutting and or plastic deformation is in the subgrade and the aggregate base. For the recalibration that currently exists in Pavement ME, there is a specific process that's kind of an addendum for what Matt originally did that was used to update those calibration coefficients. And that's why those unbound layer calibration coefficients are now soil class dependent, sands versus fine grain versus coarse grain soils. In that the LTPP sites, or the sites used in the global calibration, were segmented by asphalt concrete layer thickness. in the 3 different layers or categories were used. I'm going to say thin versus the moderate thickness versus thick, as well as the overlays and overlays of flexible pavement. So the LTPP sections were categorized into different groups. Those where the subgrade, the plastic deformation in accordance to the deformation in the asphalt layers were different, or where we know the deformation in the subgrade and aggregate base are minimal, i.e. Asphalt overlays of concrete pavement, asphalt overlays of semi-rigid pavements, asphalt overlays of thick, flexible pavements. And so the coefficients for the asphalt layers were defined, assuming that the rutting in the the base and the subgrade are nil, and then using the coefficients defined for the asphalt. And for the very thin asphalt sections, i.e. like maybe 2 inches of asphalt over in a crushed stone base, then over subgrade, those sections were used using the coefficients derived for the asphalt. Initially for the asphalt layer were used to define the coefficients for the unbound layers and whether they're soil type or class dependent, which they were found to be. And then the moderate thicknesses kind of were used, combining both those derived for very thin asphalt sections versus very thick asphalt sections, as well as the asphalt overlays, to kind of optimize what the coefficients are for the asphalt layers versus the unbound layers. So it was an iterative process, like many of the calibration for different calibration coefficients. Mostly this is going to be an iterative type process, as Wouter mentioned at the very beginning, for defining the coefficients for the layers where we haven't done forensic investigations for many of the sections, so we really don't know. So there is a strategic process that was used for rutting. There's also a strategic process that were used for top-down, bottom-up cracking for asphalt. Same type of, not the same type of decision process that were used, but the same type of decision-making process on whether it's top-down versus bottom-up was used for asphalt concrete fatigue.
Thanks, Harold. We had a couple of questions, or a few questions on the CAT website as well as documentation. The CAT website officially will be released tomorrow. We'll send out an email with instructions on registering and logging in, as well as the website URL. The documentation for the calibration assistance tool will be provided after you've logged into the application. So Harold, that brings us down to, I think, Uriah's question.
The next one on
optimize one parameter at a time.
Okay. For optimizing one parameter at a time, you can certainly select one of the coefficients and define what's the optimum value in terms of no bias and the reduced or minimum standard error for one parameter at a time. But it's generally recommended that you include multiple parameters within any one optimization set. That's really left up to the user. The calibration guide will provide some guidance on that. And I guess I'll give kind of an example, whether it's one or multiple. For Utah DOT did a local optimization study on using not many sites. They didn't have many calibration sites to be used, but one and this had to do for rutting, also for their asphalt layers. And they found that when they did the ANOVA, and there were also some questions related to the ANOVA in this webinar, but the Utah DOT did an analysis of variance to define what was affecting the residual error from total rutting. And they found the temperature was statistically significant. And so in trying to define what coefficient they should change, we know that what's significantly affected by temperature is dynamic modulus. And so on the rutting, one of the coefficients in the rutting transfer function is dynamic modulus. And so by using the analysis of variance results, Utah decided to change the exponents, the beta value for the exponent above the dynamic modulus term. And so that was used to define, quote, a localized minimum. And that was found to explain or providing most of the residual error effects. And so after they found the optimum value related to the exponent above a dynamic modulus term in the rut depth transfer function for asphalt concrete, they reduced the bias to almost minimal and reduced the standard error significantly. And so Utah then made a decision that optimum run for or optimization of the exponent for the dynamic modulus gave them satisfactory results. And so they made a decision that to select that the results from the modulus term as being their final results, and that was done. So it's basically, as Wouter said, this is an iterative type process. You're going to potentially, in most cases, use multiple parameters or considering multiple calibration coefficients of whatever distress type you're calibrating for. But the results from the analysis of variance can become very useful in making a decision on what parameters or coefficients need to be changed. And I'll mention one additional thing that relates, the analysis of variance is going to relate back to the filters for the sampling matrix. And so those have kind of been predefined for those that have been found to be significant. That doesn't mean that those filters are adequate or appropriate for all local calibrations. They will not be. I'll make that statement right now. For example, recycled versus neat mixes, Nebraska is finding that those are going to be statistically different, and that will result in different optimizations. So these filters are only the initial ones to be set up for looking or segmenting the data, and that's an enhancement that will probably be made to the calibration assistance tool down the road to let states consider other filters down the road that we know are going to be important and for individual agencies. Like what Nebraska finds may be totally different than what Missouri will find, because one state allows a lot of recycled mixes, the other does not. So I just want to make it clear that those filters are only the preliminary filters to be used, and there will be an enhancement to the calibration tool to allow agencies to define different filters of the sampling matrix that are based on their day-to-day operations and procedures, as well as how they design mixes and how they define their unbound materials. There'll be a whole host of things that will be encountered.
Okay. Got another question. Can you explain what the screen does? We were checking some of the boxes for the different descriptor items. I think that you sort of just went over that in response to this.
Right, I've already kind of mentioned that, but the results from the analysis of variance becomes important because it gives you information on what is having a statistical impact on the residual errors. And you really need to know that to know what you need to start looking at in terms of the coefficients that need to be varied. You just don't want to blindly start changing coefficients or selecting coefficients to be used, because all you're going to do is probably start confusing things. So you want to use the analysis of variance to know what is having a statistical impact on those residual errors. Remembering what I just said in answer to the other question, the analysis of variances for those terms are only those that are including in the sampling matrix to filter the data. It doesn't include other parameters that agencies are going to find to be statistically significant. Kind of just what I mentioned for Nebraska in terms of recycled versus neat type mixes. So those are only the preliminary factors. The agency still should consider analysis of variance because it's very, very important, but segment the data outside of the sampling matrix that are currently used to filter the data, because those are only the initial values. They are not the end of all for the parameters that our agencies are going to need to consider. They're only the initial ones.
Another question about the ANOVA tables. Are we rerunning ANOVA to formally separate the residuals?
You can do an analysis of variance for different portions of the sampling matrix. Right now, they can be defined automatically by the filters, but they can also, an agency can define the blocks in the sampling matrix that may not include current filters that have been established. But the user would need to do that independently of the software or the calibration tool right now.
So we had, give me 1 second here to catch up. So we had a question, can comparisons between different optimizations be made?
It can be made by the user. The calibration tool is not going to do that automatically. So if you're changing different coefficients with different runs and you have an optimal value, that optimal value being the minimum bias and the lower standard error, and you're doing that individual for different coefficients or different runs, the user would have to make those comparisons individually outside of the calibration assistance tool.
I do want to add on that, if you have multiple runs within a calibration project, you can click on each one and view how it changes. So that's there. But if you want to side by side look at it from one coefficient change to another, then you'll have to do that manually.
Next question is, the user wants to know if we're planning to offer training courses regarding the CAT. I'd say that we are planning on offering future webinars on the CAT. And additionally, individualized training can be provided through.
That's correct. That's correct.
Next question is, does the tool recommend the order of the calibration coefficients in each model, and does it give the sensitivity of each coefficient on reducing the standard error and bias? That would be down toward the bottom of this new question.
Down to the bottom.
At 11:03 a.m.
Okay, let me read this.
Yeah.
Reread it one more time. Does the tool recommend the order of the calibration of the coefficients in each model? And does it give the sensitivity of each coefficient on reducing the standard error and the bias? The tool does not do that automatically. The user will need to, but what I would say, Vooter put in toward the end of the calibration guide some kind of like sensitivity runs that will show you if you change a specific coefficient, what impact does it have on the predictions. So the user really needs to understand the transfer functions before they start making, again, blind changes in any of the coefficients and or in selecting coefficients. I'm going to refer back to the example I just mentioned for Utah. Utah understood what the effect of temperature was on the transfer function. And so then they understood that that was related back to dynamic modulus. And so they understood that then they needed to look at the coefficient or exponent on the dynamic modulus term to give them the best solution in terms of a zero bias or near practically a zero bias and the lower standard error for the solution. So the user needs to independently or externally understand the transfer functions before they start selecting which calibration coefficient they're going to change. At least that's the recommended. And the calibration guide has, at the end of it, has some of the effect of or related to the sensitivity of what each of the calibration coefficients have on the predicted values.
Okay, another question, just quickly here. We have a user wanted us to, excuse me, repeat the models used for different types of distresses. For example, linear for thermal cracking. I think you'd mentioned those in the webinar, Voter. You just wanted you to reiterate them.
I think this is more related to the form of the standard deviation residual error equations. It's not the types of, it's linear from a standard deviation of residual error standpoint. The model itself is not linear. That's what I meant by it uses the exact same form of the residual standard deviation equations in Pavement ME. You can look at that in the calibration files within Pavement ME. You'll see what the standard deviation equations are for each model.
Thanks, Oder. Okay, so when using the calibrator tool, can multiple users have user accounts? Is there a restriction to that? That's a good question. The user accounts are set up as follows. If you have a workstation license or multiple workstation license, you'll have a concurrent login available to you for each workstation license that you purchase. If your agency has purchased a site license, you'll have concurrent logins available to the calibration assistance tool up to the number of concurrent license seats that your agency purchased. A couple questions just in general. This webinar is being recorded and we'll make it available on the ME Design website. That's www.me-design.com, and it should be posted sometime tomorrow. We'll also have the presentation slides up there. Harold, this is probably a question for you. AC thermal cracking model, not working for warm climatic conditions. I guess this isn't too related, but I don't know if you want to.
Yeah, I will, and that's correct. That it's, well, I wouldn't say it's working, but are the results applicable for warm climates? And the AC thermal cracking model for transverse cracking was originally developed and derived for cold climates where you had very low temperature events, i.e. like up in Canada and the northern part of the U.S. Many agencies are in the South are using Pavement ME, and Pavement ME calculates transverse cracking regardless of where the site is in North America. So some of the agencies like Georgia, Mississippi, Texas, Arizona have many sites that have a lot of transverse cracking. If you use Pavement ME with the previous original calibration factors, Pavement ME will never predict transverse cracking in mild to warm climates. And so what but transverse cracking has an impact on IRI. That's in the regression equation for IRI. So agencies in the South wanted to include the effect of transverse cracking on IRI, even though they may not consider transverse cracking as a design parameter. So kind of a long answer to this question is some agencies wanted to be able to consider the effects of transverse cracking that they are seeing and observing on their sites in a mild to warm climate. So the decision was made in the recalibration process to find out what was having an impact. Obviously, for the residual error on thermal cracking or transverse cracking. One of the significant parameters was mean annual air temperature, and another significant parameter was freezing index. And so the decision was made to use mean annual air temperature. So that's the reason in the recalibration for thermal cracking or transverse cracking, you see that mean annual air temperature was included in defining the KT, the KT parameter, which was dependent upon mean annual air temperature, and that was done. But if you look in the addendum that was done, it was recommended that the reliability level or that the transverse cracking not be considered in design because the standard error for these areas within the warm climate, the standard error is fairly high because the mechanism is different, or we believe the mechanism for transverse cracking in warm climates is different than in cold climates, or we have very low temperature events happening. And so it was recommended that it only be included as a 50% reliability value, but that those predicted amounts of transverse cracks in warm climates still be included because of the impact on IRI. So I wouldn't say it currently does not work. The current model for low temperature events is not applicable to warm or mild to warm temperature events, but that local calibration factor or coefficient was modified to remove bias. In other words, there's no bias within the southern part of the U.S., but that the standard error is still fairly high. In terms of any progress on developing a different model for warm climates, there is going to be a problem statement. Don't know whether it'll be accepted, but it's being proposed through the task force and or through individual agencies for looking at the revising the mechanism in mild to warm climates for transverse cracks to be included eventually into pavement ME. So that's just being proposed. So we're years out from changing the mechanism within pavement ME for transverse cracks in mild to warm climates.
Okay, I think that wraps up all the questions that we had in the Q&A box here. If you watched the webinar online and you have more questions, or you just have more questions that you'd like us to answer, don't hesitate to send an email to us at pavementmedesign@aara.com, and we'll get those answered for you. You can also visit the Stack Exchange site at engineering.stackexchange.com. And that should be.
Yeah, we just have a couple other reminders. Pavement ME Design User Group Meeting is scheduled for November 6th and 7th in New Orleans, and there will be a future webinar on top-down cracking, as John mentioned, around sometime in February. As Chad just mentioned, the engineeringstackexchange.com question, we recommend all design-related questions or any pavement-related questions to be posted here. We want to increase the amount of traffic we see here and start having a pavements community on the site. Some of the enhancements for FY 2020, top-down cracking model integration, and continue to prepare for the web technology version of the software, which is a high priority for AASHTO and AASHTOWare. Thank you for attending the webinar. John, do you have anything in particular you want to say, or you all good?
I don't know if he's on the voice part anymore.
Oh.
Yeah, I think he's out.
All right.
The voice part.
This is just to kind of the contact information for AASHTO, John Donahue, the chair of the task force, Pavement ME Design Task Force, and our contact information. I just want to thank you all for attending and let us know if you have any other questions.
Thank you.